Hello, welcome back to another episode of Math with Hoss. You're watching Precalculus Season 2, Episode 22. We are continuing our investigation in trigonometry, and in particular, we are going to talk about how to find values for Arccosine, Arcsine, and Arctangent. So, a common type of problem you might get is something like this. What is arcsine of square root 2 over 2? So this is our first example. What does arcsine of square root 2 over 2 equal? Well, this is the same as asking sine of what angle theta gives you square root 2 over 2. So before, when we learned how to find values on the unit circle, we were given an angle and we plugged it into one of our 6 trig functions, and we got out a value that was in reference to the x or y coordinate, or the ratio of the x and y coordinates on the unit circle. And now we want to think backwards. So if we recall from before, sine, if you plug in an angle, it gives out the y coordinate. So when we see the problem of what does arcsine of square root 2 over 2 equal, this is saying the same thing as what angle do I get out if I plug in the y coordinate in for sine. So we are interested in what angle do I plug in for sine that gives me square root 2 over 2. Well, we know from the unit circle that theta can equal pi over 4, right? That is one value. If you plug pi over 4 into sine of, well, if you plug pi over 4 into sine, you get out root 2 over 2, right? So that means, since when we're thinking of arcsine, when we plug that y coordinate out, that means arcsine of root 2 over 2, well, that is going to equal pi over 4, because that is the angle for which sine gives you the y coordinate of root 2 over 2. It's just we're thinking backwards in respect to the sine function here. So the sine function and the arcsine, they're kind of backwards from each other. More precisely on the relationship between the two, you can see our previous videos outlining how the inverse trig functions work. I'll post links in the description below. Right now we are just kind of working through concretely what does that look like. Alright. So let's look at another example. So if we have, say, arcsine of root 3 over 2. Well, this is the same thing as asking the question, sine of what angle gives you root 3 over 2. Well, if we recall from the unit circle, that is the same thing as pi over 3. Sine of pi over 3 gives you root 3 over 2. So if you plug root 3 over 2 into arcsine, you get out the angle pi over 3. Just keep in mind that for a trig function, if it's not the inverse trig function, so something normal like the sine or cosine, you're plugging in an angle and you're getting out a coordinate or a ratio of those coordinates. For the inverse trig functions, you're always plugging in that ratio and you're getting out the angle associated with it. Alright, now we need to mention a fine detail here. So in our two answers here, we both have a single value, this pi over 3 and this pi over 4. However, if we recall the unit circle, so let's zoom out a little bit. So here's our unit circle. Here is our pi over 4. So root 2 over 2, comma root 2 over 2. and we said this was pi over 4. So sine equals root 2 over 2 out of pi over 4, but that's not all, right? I could think of this angle over here, namely 3 pi over 4. That is also where sine is positive. In fact, the y-coordinate here will also be 3 pi over 4. So why doesn't arc sine of root 3 over 2 also equal root 3 or 3 pi over 4? So why isn't this the case, that arc sine of root 3 over 2 does not equal 3 pi over 4? And we can ask a similar question about the pi over 3, right? So if I imagine drawing an arc here, well, for that arc, we know that the y-coordinate would also be root 3 over 2. So we have arc sine of root 3 over 2. Well, does that equal also 2 pi over 3? And in fact, if we think about it, we have all these coterminal angles, right? Because I can go around quantity of that angle plus 2 pi, and I can go multiples of 2 pi around the unit circle. And we know that sine of pi over 3 plus 2k pi has to equal root 3 over 2, as long as we're stating that k is an integer. So as long as we're stating that k is an integer, which is what this kind of funny notation here is saying that k is inside the integers. So k is inside the integers. So when we think about sine of pi over 3 plus any integer multiple of 2 pi, that's always going to be root 3 over 2. So there's an infinite number of values you can plug into sine and get root 3 over 2. Yet, these two values that I boxed in the sky blue color, those are the only two values that Arcsine gives out. And the reason being is this: we must remember that the domain, so the domain for Arcsine is -1, 1, but the range is from negative pi over 2 to pi over 2. And actually, we need to make that open parentheses. So, in case you're wondering why the square brackets here, this implies you're including the -1 and 1. With the parentheses here, we are excluding the pi. Actually, no, I got that mixed up with tangent. Never mind. It's been a long day. LOL. With tangent, you would need that. So we want the square brackets here because we want to include the pi over 2 and negative pi over 2. I was getting mixed up in my head for a moment with arctangent, which you would have the parentheses in the same range otherwise. But with the parentheses, we have to exclude the pi over 2 and negative pi over 2 because arctangent is actually not defined there. Because you think about tangent pi over 2, that does not exist, so it's undefined. Alright, so the reason why I brought up this tangent in the first place, pun intended, is because Arcsine has this as its domain and range. So when we think about the range, this fact right here tells us that Arcsine can only give you a value within that range. So what values can Arcsine give out? So can Arcsine equal 3 pi over 2? Oh, the answer to that question requires a red pen. And no. Can Arcsine equal 2 pi over 3? No. Reason being is because those are all outside of the range of Arcsine. So in the previous videos, we talked about how we had to do these range restrictions because otherwise Arcsine, Arccosine would not be a function. In fact, we saw on Desmos, if we just use that nice graphing utility, if you wanted to graph arcsine cosine, it just looked something like this for all of infinity until we did a restriction of their range. In fact, we can just pull that up right now. Take a look at that. So, how about x equals sine y? See there? That is why we did our domain restrictions. In fact, here's arc sine x. And you see, we're just using that little bit right there. Alright. So enough of decimals. Boom. Okay. So that's one thing you have to keep in mind with the inverse trig functions is that they all have restricted ranges. And that is so that for every x value you plug in, you only get out one output. Every input gets a single output, in this case here. And that is just so we prevent the problems of our functions not actually being functions. Alright. So we can apply this process to Arccosine, but let's look at an arctangent problem now, because those ones are usually the trickier ones. So let's zoom back in. So new example. Suppose we were given arctangent of how about root 3? Let's make it negative root 3. Okay, so the way you want to think about it is this. When you think about your unit circle, you have two basic types of, or you have three basic sets of points. You have points with zeros and ones, you have points with root 2 over 2, and you have points with root 3 over 2s and halves. Those are your three basic sets of points, and the x, y values just alternate between those values, positive or negative, depending on the quadrant. So the first thing we need to think about is the fact that we have this root 3. That root 3 tells us, well, the only coordinate pairs that have root 3's that we're dealing with is these ones here. So that tells you automatically that we're going to be dealing with something like a pi over 6 or something like a pi over 3. And I say something like because we still have to determine the quadrant and everything. That brings us to our next fact. So we see a negative here. We need to go back now and think, when is tangent x negative? We want to think, when is tangent negative, because what we have here is the output being negative. So we want to think, for what inputs for a normal tangent do we get out a negative output? Now tell us something about this arctangent and where our answer is that we're interested in. So when we think about the unit circle, so we can note that tangent is equal to sine over cosine. So when we think about quadrants 1 and say 1 and 3, tangent has to be positive, because in these cases both sine and cosine is positive for quadrant 1, so this is quadrant 1. And for quadrant 3 here, sine and cosine are both negative, which means that negative number divided by negative number is positive. So we are interested then in either quadrant 2 or 4, because that is when either sine or cosine is positive and the other one has to be negative. So in quadrant 2, for example, sine is positive but cosine is negative. In quadrant 4, it's the opposite. The other thing we need to keep in mind now is we are interested in the inverse trig function, the inverse tangent, arctangent. Arctangent has a range only in here. Actually, maybe we should use a different color. So the negative tells us our answer has to be in one of these two quadrants. And now let's state the domain, or I mean the range. Range of arctangent, which we talked about a moment ago, was from negative pi over 2 to pi over 2, open interval. So that means that these two possible shaded quadrants, we are dealing with this one right here that I just shaded in green. Okay. So we know our coordinate pairs have to be this right here. Has to have a root 3 over 2 in it. Reason being is because we looked inside the arctangent and we saw a root 3. Next, we saw a negative sign that tells us either quadrant 2 or quadrant 4, because that's where tangent is negative. But because we know the range of arctangent is from negative pi over 2 to pi over 2, it has to be in quadrant 4. So this leaves two possibilities. Negative pi over 6 or negative pi over 3. Question now is which one? So if you didn't know, you can just guess, right? So negative pi over 6 has the coordinates of root 3 over 2, comma, negative a half. And negative pi over 3 is negative a half, comma, oh, no, that's positive a half, negative root 3 over 2. Got that mixed up in my head for a moment. Alright. So we know it has to be other possibility. And how we want to think about it is we have the ratio here, right? So let's think about it. Scroll out a little bit. Alright, so we know tangent is equal to sine over cosine. So if you didn't know any better, well, you can always just try something, right? So if we think tangent of pi over 6 negative, alright, well, this has to equal, see your sine is negative a half over root 3 over 2. So that's going to equal negative 1 over root 3. That's not what we want. So then if we think about tangent of negative pi over 3, well, that's equal to negative root 3 over 2 over a half. And notice these 2's cancel out, leaving you with a negative root 3 over 1, which is what we want. So essentially what we're doing is doing a reverse thinking process. So this is actually our answer right here, negative pi over 3. Negative pi over 3. So we start by noting we had a root 3. The root 3 tells us we have to have this highlighted blue as our possible coordinates. Either the half is the x coordinate and the root 3 over 2 is the y coordinate, or the other way around. We saw that the range required us to be in quadrant 4 when we also considered the negative. And then it's just thinking about the ratio, right? So tangent's always a ratio, which means we want to think about when does, well, in this case we want to think about when is the root 3 in the numerator. Well, that has to be when root 3 over 2 has to be in the numerator for sine, and we saw that work right here in blue. Alright, so that kind of gives you an idea how to handle a tangent problem. They're weird, but they're also kind of fun because you have all these little different pieces to tear apart. Let's do one more tangent example. So, example, suppose we have arctangent of negative 1. Well, this is going to be similar now. So our possibilities is 0, 1, root 2 over 2, root 3 over 2, comma 1 half. So because we're given a negative 1, you know it can't be the one on the bottom, because you have this root 3 hanging out, either numerator or denominator, so that's awkward. And you know it can't be this case here, because the only time arctangent uses those coordinates is when tangent of the angle is equal to 0. So in other words, it only works for pi and 0 and their multiples. or I should say coterminal angles. So that means you have to think of this one, but that seems weird at first. But if we think of it this way, tangent x is equal to sine x over cosine x. If you were just to plug in, if you were to call that sine cosine equals root 2 over 2 at pi over 4, for example, like tangent of pi over 4 is equal to sine of pi over 4 over cosine of pi over 4. So if we recall that for a moment, then, well, sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. But hey, notice it's the same thing. So these die off, and it just leaves you with a 1. So notice, when we just have the root 2 over 2, when we have a 1 or negative 1, that means we are interested when the sine and a cosine have the same value, just a difference of plus or minus. So, to review, let's make our unit circle. So, arctangent tells us we have to be in one of these two quadrants. The negative tells us we have to be in this quadrant. The root 2 over 2 tells us it has to be either pi over 4 or negative pi over 4. And that is because pi over 4 and negative pi over 4 are the only two values in either quadrant where they cancel out, leaving us with plus or minus 1. So just to recall, for negative pi over 4, we have root 2 over 2, comma, negative root 2 over 2 as our x and y coordinates. So, arctangent of negative 1 has to equal negative pi over 4. Alright. And before we wrap up, I do want to make one note. These three functions, arcsine, arccosine, arctangent, are all programmed in your calculators here. So usually if you have a scientific calculator, what you need to do is hit a button like second, and then if you just click on your trig function, now we have arcsine. Yeah, I don't know, let's just plug in some 0.65. There we go. And we get some value. Cool. And if you want to make your calculator cry, you can plug in something like, how about 9001, because it's over 9000, and there we go, calculator cries, error domain. And that should make sense because we mentioned already that Arcsine has a domain of between -1 and 1. So if you want, we can do arctangent, figure out what is arctangent of 9001. And what do you know? You get something that's almost pi over 2. And if you're wondering why that's the case, we actually talk about that. And we can recall that if you think about the ratios here, as we get closer and closer to pi over 2, as the ratios of, you get y divided by x, right? The y values are getting closer and closer to 1, but the x values are getting closer and closer to 0. So you got a number like 1 divided by a number like 0. So if you take like 0.99999 and divide by something really small, I don't know, we're just going to make something up, 0.999 divided by 0.000. I don't know. When you divide by a really small number, you get really big numbers. We got 1 times 10 to the 13th. So that's really what's going on. As our values get closer and closer to pi over 2, our xy coordinates, this ratio, as you get a number closer to 1 in numerator, divide by a really small number approaching 0 in denominator, that ratio is going to get larger and larger towards infinity. That's why tangent works, but not the other two. Alright. If you've enjoyed this video, please consider subscribing, supporting us on Patreon. Thank you for watching, and I will see you next time.